I'm going to introduce Willow Martin. So everyone, please welcome her and welcome to the Rise Hub seminar. So Willow is from Siegfried Glenzer's group at Stanford University. She's a PhD student, and she will be giving a talk about time-resolved X-ray spectroscopy and imaging for IFE target design. And so, Willow, go ahead and take it away. We're all excited to hear what you have to present.
Cool. Thank you for the introduction. Good morning, yeah, good morning. I will assume everybody's on the West Coast like me, which might be naive. But I'm Willow. I'm a PhD student and experimentalist at Stanford and SLAC. And today, I'll be giving you all seizures with these very fast GIFs. In addition to that, I'm going to be showcasing how we use the high peak brightness X-ray pulses of the Linac coherent light source, or LCLS, to study the rapid evolution of polycrystalline diamond, depicted on the left-hand side, and polymer foams, depicted on the right-hand side. Materials which are highly relevant to the ongoing ICF campaign and future IFE target designs. So without further ado, we'll just launch right in with some context. So despite the many startups that are popping up today, in our solar system, there is still only one fully functional fusion power plant online, the sun, and their gravity provides the confinement, compression, and heating required for fusion. To produce fusion energy here on Earth, we must create and control a plasma hot and dense enough to ignite, and then confine it long enough such that the energy released exceeds the energy we supplied into the target to initiate fusion reactions. This grand challenge was overcome in 2022 when a fusion implosion experiment at the National Ignition Facility, or NIF, achieved a target gain of 1.5. In the ongoing ICF campaign, NIF ignites targets via indirect drive, holding a DT-containing capsule in a gold can called a hohlraum. So nowadays, these targets consist of a diamond capsule, which holds the DT fuel inside as an ice layer, and a vapor fill. While ignition has now been achieved and repeated, I have an 8.4 megajoule sticker on the back of this laptop I'm presenting on. These experiments are rife with failure modes. For instance, hydrodynamic instabilities have to be controlled since they can mix material and inject high Z ablator material into the hotspot, amplifying radiative losses. For example, even micron scale imperfections in these sorts of experiments can seed instabilities that grow and prevent ignition. So extreme care is taken to ensure target quality. So much so that this ice layer that you see in the center is actually fabricated as a single crystal. It's grown over many days in a process called beta layering. But in a future IFE, or inertial fusion energy facility, beta layering of a DT ice inside of a shell is not going to be viable. It's slow, challenging, and incompatible with the low tritium inventory that's preferable in a fusion power plant. So this necessitates the exploration of wetted foams, as shown on the right-hand side, or other fast-filling techniques. So while polymer foams are a leading option for housing nuclear fuel and IFE targets, they present their own suite of challenges. To design robust IFE targets, we need accurate equation of state models for each material that we field. These models then get plugged into hydrodynamic simulations to predict their behavior at high energy density. But because of the high computational cost, most foam EOS modeling neglects its microstructure and evolution under shock compression or heating. So it's critical that we acquire data to characterize the homogenization of foam microstructure and its effect on the overall equation of state of material as a function of time. Now, in the experiments that I'll talk about for the remainder of this talk, we were interested in characterizing thermodynamic behavior and mesoscale behavior. To give a bit of context, since this is a student seminar, I'm going to take a few slides to go into some of the thermodynamic focused, EOS focused diagnostics that we fielded in this experiment, which maybe is a little baby for some people on this call, but nonetheless, I'll just take a bit of time to go through some of the diagnostics that we fielded in this suite of experiments. Um, our more challenging diagnostics that we were aiming to optimize were focused on measuring the temperature and density of underlying material heated to high energy density states. There's a dearth of temperature diagnostics that are applicable at high energy density, which kind of motivated us to focus on these diagnostics in the first phase of our campaign. And there's an even more limited suite of temperature diagnostics available if you want your temperature diagnostic to actually probe the interior of your warm dense matter or hot dense plasma. For that purpose, X-rays are advantageous because they can, you know, escape the target volume without significant attenuation. And in our experiments at LCLS, we experimented with two different kinds of temperature diagnostics, namely X-ray Thompson scattering and X-ray fluorescence spectroscopy. So in both, we probe the plasma with X-rays and collect spectra characterizing the radiation's interaction with electrons. For example, by scattering off of free electrons, so if you look at the lower left-hand quarter, um, you can characterize the electron velocity distribution and use that to back out either a temperature or density, depending on how degenerate your plasma state is. While X-ray Thompson scattering measurements will intrinsically integrate along this, will integrate the scattering signal along the path of your X-ray probe, measurements made via an alternative diagnostic, namely X-ray fluorescence spectroscopy, are inherently localized to whatever region you select to dope with a mid to high Z tracer material. That's the material that you go in and excite K-shell electrons from, um, setting off fluorescence interaction that you can then measure and use to inform your interpretation of the underlying plasma conditions. To accurately model scattering and fluorescence spectra, we need to account for a variety of atomic scale processes, which thankfully we have codes to do on both fronts. So namely, I've been using multi-component scattering codes for analyzing X-ray Thompson scattering spectra, and atomic kinetics codes like Cretan and Scram to analyze fluorescence spectra. I've included some such synthetic spectra here to prove to you that I'm not lying and that we actually have these codes. And I can highlight the temperature sensitivity of each diagnostic by pointing to these synthetic spectra. So X-ray Thompson scattering, to give a little bit more context, can determine not only temperature, but density and potentially ionization with a high degree of precision, depending on the signal to noise ratio of your data, of course. But depending on the scattering angle, you can access two distinct scattering regimes, non-collective or single particle scattering, which provides direct access to the electron temperature and densities via the shape and the width of the Compton feature, this inelastic feature downshifted from the elastic peak. And collective scattering, where coherent plasmon oscillations encode information about electron density from the plasmon dispersion and electron temperature via the detailed balance principle. On the other hand of this plot, we have synthetic spectra simulating fluorescence spectra from a cobalt doped sample. Fluorescence energies are primarily a function of electron binding energies. So photoemission spectra can determine the ion charge state distribution and then via atomic kinetics modeling, the underlying plasma temperature. So highlighted on the bottom right-hand quarter of this slide is a plot kind of summarizing that temperature sensitivity of different fluorescence lines. Note that the temperature sensitivity varies depending on the emitting material and atomic transition. But this predicted sensitivity helped inform the target and diagnostic design in our first round of experiments at LCLS, which were conducted last year. So in this first round of experiments, we paired the MEC short pulse laser with a synchronized free electron laser to study the evolution of a variety of laser-heated samples. Laser heating, direct laser heating, deposits energy rapidly into the target without significant compression, offering flexible access to warm dense matter conditions and far more shots than shock compression experiments, certainly at NIF and even compared to other shock compression experiments at MEC, where there's a of order 10-minute turnaround time between shots with the long pulse laser. The challenge with probing these sorts of states is that they evolve quite quickly as the target hydrodynamically expands. So capturing the interesting physics when the plasma is as hot and dense as it can possibly be requires diagnostics with sub-picosecond resolution, um, which XFELs can uniquely provide, hence us going to LCLS. So the aim of this first LCLS experiment was to test multiple temperature diagnostics, namely X-ray Thomson scattering and X-ray fluorescence spectroscopy, under a range of conditions. And if you've ever seen previous talks of mine, you've already heard me speak at length about each um, diagnostic in detail. So I'm going to, for the remainder of this talk, focus more on the actual data we collected. So at LCLS, our design was set up to detect K-shell fluorescence from cobalt dopants while simultaneously capturing X-ray Thomson scattering signals from the bulk of the target. In our design, a mosaic crystal spectrometer measured non-collective scattering. Right here, if you can see my arrow, which I suspect you're not able to, so I'll just articulate through it. In pink, that's the mosaic crystal spectrometer, and in teal, I'll say, is the high resolution spectrometer, which we use to measure distortions of the K beta line. So by varying the laser intensity, probe delay, and sample composition, we, in the course of this beam time, studied the dynamic evolution of various carbon-rich samples. For example, we observed, as shown in the center of this plot, measurable blue shifts in the cobalt K beta signal from cobalt-doped graphite, confirming its sensitivity to temperature-driven ionization. The high emission cross-section allowed us to operate in a single shot mode. So we could analyze single shots using their fluorescence spectra, which allowed us to scan probe delays quite quickly to pinpoint optimal timing to detect signatures of heating as shown in the top red line out. Then using the atomic kinetics code Cretan, internal to Livermore, to model the emission shift, we inferred a temperature of 51 eV at a 50 picosecond time delay after heating with a joule of laser energy. Now, after studying doped graphite, we lowered the laser intensity to reduce our background levels and focused on collecting X-ray Thomson scattering spectra from our undoped samples. And in this backscattering geometry, the inelastic X-ray Thomson scattering feature shown peaking, around 7.9 keV, is sensitive to both electron density and temperature. Under the assumption that the heating was isochoric, which it should be at these early time delays, these are 5 picosecond time delays shown on the right-hand side, we inferred a plasma temperature in diamond of about 60 eV using a Bayesian fit with Markov chain Monte Carlo sampling. These data collectively in this campaign demonstrated that fluorescence spectroscopy and X-ray Thomson scattering can provide independent and complementary constraints on plasma temperature, where fluorescence spectroscopy has the advantage I mentioned earlier of being able to be localized, but as you saw in previous slides, has a downside of being less sensitive in lower temperature regimes, namely 10 EV and lower. So the results of this platform development experiment were very exciting and are the subject of a published POP from 2025, I think it came out, so this year. But this experiment, more significantly for this presentation, laid the foundation for precision studies of diamond and polymer foams that we completed this year. However, to reduce uncertainty in our forward modeling of our X-ray Thomson scattering spectra of foams and any other samples, we wanted to more carefully account for potential hydrodynamic expansion of our target, since particularly for foams, their large surface area will enhance the effect of expansion on the overall bulk density. So to reduce that free parameter that gets fed into the forward modeling, we added imaging to more directly constrain the homogenization of our foams when we shot those samples in particular. So in particular, in our very recent follow-up campaign, we added the MEC X-ray imaging setup, or the MXI, to our platform. We used a stack of 20 beryllium lenses to produce a magnified X-ray image of our target The total magnification was about 60 and combines the X-ray magnification provided by the beryllium lenses in vacuum with the optical magnification provided by the objective. This provided a sufficient field of view and resolution to resolve multiple foam periods in our targets, which I'll show the actual data from a little bit later. So in summary, during this experiment, we operated in two modes. One optimized for imaging, in which we defocused LCLS to ensure uniform illumination of our targets, and another mode that was optimized for spectral measurements, where we focused LCLS back down to a 5-micron spot to ensure we probed uniform conditions heated by the MEC short pulse laser. So with a focused LCLS, we collected scattering signals in both backward and forward geometry this campaign to access regimes with different sensitivities to non-collective and collective modes. Using these diagnostics, in the end, we characterized the evolution of polycrystalline diamond, which provided really high signal-to-noise ratio data, and polymer foams, which will be challenging to analyze, but we have a much stronger hold on now thanks to the imaging. So I have slowed down the GIF by turning myself into the play button. So I'll march through the images that we collected on diamond to start. This experiment happened quite recently, so analysis is still in a preliminary phase, but I can share with you all a first look at the images and spectra that we collected. So starting with diamond on the left-hand side, there are images of the targets before on the left and on the right after being heated with a joule of laser light. And after rapid heating, we observed mesoscale structure evolving out to 10 nanoseconds. So let me just continue marching through all of the data. So these images are in a refraction dominated regime and are particularly sensitive then to changes in the index of refraction, which can be induced by changes in density or temperature. And the light and dark fringes that you see in these images pick out abrupt changes in the sample in one of those two plasma conditions. So in the next stage of analysis, we're going to aim to understand whether these signals depict the complex filamenting and bubbling structure of the ablated plasma plume from our sample, or if it originates from the evolution of grain boundaries in the remaining bulk of the solid density sample. These images are complemented by high signal-to-noise ratio scattering data. So as in the previous experiment, the inelastic feature will encode information about the density and temperature of the underlying sample, but the information content we have here is richer still. So even without full forward model fits, I can tell you a little story about this data just from looking at the evolution of the elastic feature intensity relative to the inelastic and some edge features that are appearing in the spectra. So I'll take you through the story just to kind of highlight the power of this diagnostic and the exciting components of this data set. So in less than a picosecond, going from gray to purple, you can see evidence of rapid disordering of the crystal lattice, given the fact that there's a sudden jump in the elastic feature intensity in both the forward and the backward. So in the forward, it's very, very subtle. It's basically impossible to see. And in the backward, this peak here, that is the more conspicuous elastic feature. And jumping up to a picosecond, you see that the peak, that elastic peak, is much higher with respect to the inelastic scattering feature on the left-hand side. And this is because when you disorder the lattice in order to elastically scatter, you no longer need to meet Bragg criteria. You have a more amorphous sample that allows for a much higher elastic scattering cross-section. Then you can watch that feature evolve in time further. And the interpretation of this feature evolution that we've come to is encodes evidence of recombination occurring at late times in our sample. This interpretation is corroborated by forward scattering data. So we see coinciding with this jump at late times in the elastic scattering feature intensity, which would indicate that there are more bound electrons that can contribute to elastic scattering, therefore recombination happening and less ionization. We have, if you have a really excellent eye, evidence of this also in the forward scattering data, where you can see kind of right at the end of that 10 to the third picosecond text box. If you look subtly at that spectra, and I can show you this on a log scale later where it's a lot more conspicuous, there's a very fine change in the overall intensity. And that what you're seeing is the carbon K edge. So we, in this data set, can track the position of the carbon K edge, which will shift around very sensitively as a function of the ionization degree of the underlying carbon. And the position of the carbon K edge that we observe in the forward scattering spectra um, indicates that the ionization degree has also dropped significantly between 100 and 1,000 picoseconds, as is also indicated in the backward scattering data. You can see we observe a different trend in the overall elastic to inelastic scattering feature intensities in the forward. There we're working on the interpretation, but there are a couple of possibilities that encode information either about a rapidly decaying ion temperature or potentially a return to a more crystalline state as compared with what we have at early times. So we have to better understand the evolution of the static structure factor in order to um, pinpoint an explanation for this monotonic decay in the elastic scattering feature intensity as observed in the forward. But we have strong handles on the data given the fact that the data is so high signal to noise ratio. And so we're focused on this analysis to start before we march into the more directly IFE relevant foam data. So in this campaign, we also scanned a time history imaging the collapse of pores in 2PP or two photon polymerized foam lattices. These data directly target the primary source of uncertainty in our inference of the plasma temperature, allowing us to understand the timescales on which we expect a significant change in the overall density of the sample as we transition from solid density struts to a homogenized foam over the course of a nanosecond. So while the signal to noise ratio of our foam scattering data is lower than it is in diamond because of need to accumulate more to reach the same number of scatterers, I want to highlight that the multi-angle X-ray Thompson scattering spectra will and can be fit simultaneously to offer a tighter constraint on the inferred plasma conditions as compared to the data we collected last year. So we have uh, additional constraints, not just because of the imaging, constraining the rate of homogenization, but also this multi-angle scattering. And we can compare these data directly with radiation hydrodynamic simulations, such as the one I'm depicting on the left-hand side, to kind of model the expansion of these struts and make comparisons with theory. So with the remaining time, I'll give a little bit of a broader context for these experiments too, in the context of my work more holistically as a student. So this experiment I actually originally proposed to lay groundwork for experiments that we conducted and will continue to conduct at Omega. Namely, the diagnostics that we fielded in the first stage of our campaign at LCLS, X-ray Thompson scattering and fluorescence spectroscopy, were also fielded at Omega last year to characterize imploding targets that were directly driven with about 14 kilojoules of 351 nanometer laser light delivered by the 43 shaped drive beams at Omega. Here, the target is heated not via direct laser heating, but by compression using long pulse lasers, and is probed by hard X-rays generated by a zinc helium alpha source, a zinc backlighter foil. So after collimating these X-rays through a slit, which sat in our half cone configuration, X-rays propagated through our converging solid and foam targets to characterize the plasma conditions using a combination of fluorescence spectroscopy and X-ray Thompson scattering. We faced a lot of challenges in this experiment because our framing camera was broken for half of the day. But when we could collect data, we were able to simultaneously observe scattering signals and fluorescence signals and we're able to collect a data set that we're using to design the experiments that will follow up on this campaign in June of this coming year, where we'll once again study doped and undoped polymer foams using cobalt, as was used at LCLS, and iron as our underlying fluorescence surrogate material. For even more context, this work kind of exists in a body of work that I'm participating in, which spans multiple facilities. We recently had a campaign at SLAC collecting high signal-to-noise ratio data that can validate atomic kinetics modeling of various mid-Z materials such as iron. I mentioned the Omega campaign that's coming up in June, where we'll once again study cobalt and this time iron-doped polymer foams to focus in on adiabat measurements of converging foam capsules in particular. And to give a kind of final look ahead, we were actually just recently awarded time at the National Ignition Facility via the Discovery Science Call to extend our studies of doped polymer foams towards wetted doped polymer foams for astrophysics applications. And that's a whole presentation onto itself. So I'm going to finish by highlighting the synergetic work of my colleagues at SLAC, who I certainly rely on as experts in the field for designing experiments and analyzing data. And it's this collective work that has built up the capabilities in our group to provide the baseline for these future proposals on wetted foams, both at NIF and at other facilities. So this will look familiar to some of you, especially Daniel. Uh, with that, I'll leave my conclusions up, and I'm happy to take any questions. I know I threw a lot of data at you all during this presentation. Um, and yeah, should I have more time, I would love to, do a presentation at some point with with the complete analysis of the LCLS data, but it was collected so recently that it's still in a preliminary stage. But I'm happy to answer questions about that or any of the other experiments I mentioned.
Awesome. Thank you, Willow, for that great presentation. If everyone could join me in just clapping, thanking Willow for giving a great presentation, that would be awesome behind your screens. Awesome. Yeah, we'll open it up to questions. I do have a few. So if anybody has a question they want to jump up and ask right now, in case some of you have to go for it before I ask my questions. All right, I will proceed with my questions then. All right,
Okay.
so yeah, so earlier there are some plasma diagnostics that you do to determine like the electron density and temperature, like in your beginning slides,
Mhm.
with the Thomson scattering that you were talking about.
Yes.
Um, do you need the combination? Like, how do you determine that density and temperature? Is it just the free electrons, or do you need the combination of the free and bound electrons? I'm not really familiar with like the plasma diagnostics aspects. I'm just like the X-ray imaging person. So
Yeah.
if you could like expand on that and help me understand that a little bit better, that'd be awesome.
Yeah, of course. So I think the easiest one to get a handle on, or the easiest two to get a handle on, would be non-collective X-ray Thompson scattering.
Mm,
So if you look at the upper left-hand side here, the
yeah.
primary constraint on electron temperature is coming from the inelastic feature, in particular the free-free feature. Let it go back a slide. There are three primary contributions to X-ray Thompson scatter spectra that you can decompose. That decomposition, if you've heard of it before, is something called the Gihara decomposition, where basically you calculate the contribution to scattering from three different kinds of interactions. So you can have your radiation interacting with bound electrons
Mm,
that remain bound after that interaction. Those interactions make up your elastic scattering feature, so that very sharp spike at your probe energy. That's actually very difficult to model correctly. So usually people
mm,
just treat it as a Dirac delta spike and convolve it, though there is ongoing significant effort to make more sophisticated models for that, which hopefully will apply in this data analysis. Then another class of interactions you have to consider are bound-free interactions, where radiation comes in and effectively ionizes electrons that were originally bound to an ion. And those kinds of interactions, just like you're probably familiar with edge features that appear when you're trying to calculate like best filtration, you kind of
Mm.
similarly get an edge feature here, where there's a gap between your elastic feature and your bound-free edge. So the contribution to the scattering signal in this regime is coming from electrons that were sufficiently energetic to ionize K-shell electrons from the carbon. Lastly, we have the free-free interactions where the radiation interacts with the ionized electrons. And that's really where we get our strongest constraint on electron temperature because we're
Okay.
directly probing the distribution function of these electrons. In principle, the distribution function will depend on both the electron temperature, characterizing the velocity, or if you're in a very degenerate state, it will also depend sensitively on the mass. And usually when we're operating in a warm, dense matter regime, we're somewhere messily in between the two. So that's where we get our primary constraint on electron temperature via X-ray Thomson scattering. Um, in at least the non-collective regime, and I'll kind of focus on that for now. Um, on the right-hand side, we have a diagram for fluorescence spectroscopy, which I've argued can also serve as a temperature diagnostic, but there is more model dependency built in there.
I see.
So in order to calculate fluorescence spectra, you really need a detailed atomic model. And you need to calculate the rate equation, which would tell you how ionized you expect your plasma to be under certain plasma conditions. So given a temperature and a density, you can calculate with a detailed atomic model and atomic kinetics modeling what your expected degree of ionization is, and therefore what energy you expect your fluorescence feature to appear at. You can stop me and ask a question there if you.
No, yeah, no, no. I think I understand a lot better now. Yeah, thank you for
Yeah,
diving into that. I appreciate it.
of course.
Um,
So you parameterize the temperature and the density, and you get out synthetic spectra in the end.
yeah, cool. I do have other questions. Does anybody want to ask questions before I ask more? And I will also, after I ask my couple questions, I will turn off the recording. And for those that are not comfortable with asking questions during the recording, can then ask questions during that point. So, does anybody have any questions they would like to ask Willow? Then I will proceed to ask another. Okay,
Mhm.
so you mentioned like the hydrodynamic simulations, and I'm familiar with a few of them. Like there's like Flash, there's like X-Rage, Hydra. But you in one of your slides you said it's an NLTE rad Hydra. What's the NLTE? Like what is that? Is that like non-linear some like I don't know what that is. Maybe I missed it.
Yeah. So LT is local thermodynamic equilibrium, and NLTE means
Mm,
not that.
yeah.
Non-LTE. So when I say NLTE, it's a good question to ask because uh, defining LTE and therefore defining NLTE is kind of challenging. People have different definitions depending on what kind of equilibrium they care about. When I talk about NLT here, I just mean that the electron and ion temperatures are evolving independently of one another. Um,
Oh, okay.
so they're initialized separately in these hydrodynamic simulations because short pulse laser heating preferentially heats your electron population as opposed to your ions. So if you're to try to model the heating. I mean, at short time scales, you would need something like PIC. But if you are interested in evolution out at longer time scales, you can, for these short pulse lasers, assume rapid energy deposition in a short time early on. and then just use that as an initialized condition for the subsequent evolution of your target. So here in these hydrodynamic simulations, I initialize the electron population with some elevated temperature and leave the ions at cold and let the two populations evolve independently. You'll see if you track the electron and ion temperature as a function of time. In a solid density sample, they would just kind of equilibrate
Mm,
quickly and then track with one another. But what's interesting about these foams is that when you have your strut expanding and then colliding with neighboring foams, you can actually drive up the ion temperature beyond the electron temperature. So you kind of overshoot that equilibrium point and then eventually slowly, once you're homogenized, come back down to an equilibrium. Jose Milovich has some really interesting simulation work on this too for
yeah,
subcritical density foams.
cool. Yeah, the last question that I have
Mhm.
is so in your one of your experiments you did a short pulse laser to hit your target, and then at Omega you mentioned that you do a long pulse laser.
Yes.
Like how I guess what makes you determine like which pulse laser to use and like what circumstance? Like do you know much about that you can expand on for those here and maybe new graduate students perhaps that are getting into plasma physics?
Yeah. So it depends on a lot of different factors. So I proposed experiments at MEC first for a few different reasons, but there I wanted to do something an experiment that explored a wide range of plasma conditions. And that's why, for this particular MEC experiment, we proposed at LCLS and we proposed to use the short pulse laser
Mm.
because we were trying to validate the performance of fluorescence spectroscopy as a diagnostic, but it was in a very new sort of temporal regime for that diagnostic to be applied. And there was, an additional challenge that we faced in being ill-constrained and being able to predict the plasma conditions that we would generate. Um, and let me try to. So we, in that MEC experiment, wanted to design it such that we could operate at high repetition rate, so we could scan out a range of different parameters and look for the conditions where fluorescence spectroscopy operated optimally. If
Oh,
we
I
were to
see.
go to an experimental facility like Omega, we can get a lot of relative to some other facilities, meaning that we can get a lot of shots off in a day, but not enough to really do a fine scan of parameter space with many different materials and many different drive conditions. So at LCLS, we took hundreds of shots. At Omega, we took four and a half shots, depending on how you count. And you can get more off at Omega, but if anything goes wrong at the facility, you can very easily lose half your shot day. And so grid scans at Omega are not optimal. There we were aiming to use the diagnostics that we validated at MEC. So I would say my advice would be to anybody who's an experimentalist who's looking to do their own experimental campaigns, and you're trying a novel diagnostic or really anything novel, but I would say diagnostics especially, try to validate it on smaller scales before going to the biggest and slowest facility that you have available to you.
Mm, cool. Thank you for answering that.